Alright, hello everyone. So here is the second stream out of 3. Again, so if you're joining for the first time here, essentially what happened was this morning, since my class is taking finals, I figured other people are probably going to take finals too, I decided to stream. So I'm just reviewing all of semester 1 for AP Calculus, AB, and BC together. At least what I covered in my class for AB and BC. So chances are you covered about the same type of stuff if you're not in my class and you're watching this. But if not, then, well, you'll learn some stuff probably. Alright, so you can see the stuff that we're going to do here is basically applying derivatives. And then we're going to get into basic evaluating integrals. So I'm actually about 30-ish minutes ahead of schedule, so we'll see if I need a break after this or if I'm just going to keep going. Alright, let's begin then with the notes. Okay, so instead of just going over here's the first derivative test, here's the second derivative test, and stuff like that, what I like to do is think about, okay, what do these things even mean in the first place? And then from there, derive the derivative tests. So, f prime, what does it tell us about f? What it tells us is the rate of change of f with respect to x. Okay, so what happens if f prime is negative then? That means the rate of change is negative. In other words, f is changing at a negative rate. In other words, f is decreasing. So what about if f is positive? F prime is positive, sorry. Then similar thing, except obviously the rate of change is positive, so it's changing in a positive way, right? So that means f of x is increasing. So that's pretty clear, like opposite behaviors. What about if f prime equals 0? Then it's neither increasing nor decreasing, but instead f of x is what's called, has a critical point. So a critical point is where f prime of x equals 0 or f prime of x doesn't exist, does not exist. So it has a critical point, and that also means maybe a max or min. Okay, so let's look at the second derivative then. So this thing, it can tell us basically increasing and decreasing, as well as max or min potentially. And you can just kind of check to see things later on. Basically, if you have a potential max or min, let's just say this point is maybe a max or a min. On the left of it, the function's increasing. On the right of it, the function's decreasing. What would this be? Obviously a maximum. Kind of think of a roller coaster. If you go up, then down, the point where you change is the maximum. Versus if you have a point and you're decreasing on the left and increasing on the right, that thing's got to be a minimum, right? So just logic. So the derivative test and all that stuff is actually just a lot of logic. So think about it that way and that'll help. Alright, f double prime. That tells us the rate of change of the rate of change with respect to x. So in other words, how do the slopes change? So if f double prime is less than 0, that means the slopes are decreasing. So imagine a function where here's one slope, and then another slope, and then each slope has to be getting more and more negative, right? Or like, it's really positive, then it starts to get negative. Just get smaller. So you get a curve that looks something like that. Or a part like that, or a part like that. So what we actually call this is concave down. So f of x is concave down. And then this opposite behavior. So obviously this is going to be concave up. So let's think about why that is though. the function is going to be having increasing slopes. So let's just say we had some slope like this. The next slope would be more positive, so something like that. And then notice that each of these slopes I'm drawing are getting more and more positive. They're getting greater, they're increasing. So if a curve looks something like this, that means it is concave up. In other words, f double prime is greater than 0. When f double prime is equal to 0, f has a point of inflection. So make sure you write this word correctly. Inflection, not infection, not injunction, not injection, or anything like that. I've seen that before. Apparently that's happened on the AP test as well. So yeah, make sure that that is correct. But essentially what that means is f double prime can change between concave up and down. Whether it does or not depends on basically... So like, here's an example where the inflection point clearly changes from concave down to up. But you can also have the case where that doesn't happen. Essentially, the function is concave down. And a point of inflection could be where the function, where f double prime is undefined as well. So you can have something that's like concave down, and then asymptote, and then concave down still. So that still happens. Alright, let's move on to the derivative tests. So here's the first derivative test as it normally is written. And the goal for the derivative tests is to find extrema. So, if f is continuous and differentiable, and x equals c is a critical point, then... Okay, so let's just look at what this means in terms of meaning first. F prime is less than 0 on a to c, and f prime is greater than 0 from... Oh, that's supposed to be c to b. Whoops, let me change that real fast. That's supposed to be c, that's supposed to be c. Basically on the left and the right of c. So this means increasing to decreasing, right? So if you have increasing to decreasing, as we said up there earlier, then you have a... decreasing to increasing. I'm sorry about that. Decreasing to increasing, you get a minimum. And then if you look at the thing below it, you see f prime is greater than, and then f prime is less than. So greater than, then less than. So increasing, then increasing, then decreasing. Then you get maximum. So just kind of think about it logically, think about it physically if you need to, and you'll see that it'll make sense. Instead of trying to memorize this theorem, no. So increasing to decreasing, max. Decreasing to increasing, minimum. If it doesn't change at all, then it's neither. So an example of that would be this, the x cubed function. At 0, it has a derivative of 0, but it just keeps increasing, right? This is what's called a saddle point. You will not need to know that for the AP exam, but it's just useful to know, especially if you're going into one of the STEM fields. It's just called a saddle point. Alright, second derivative test then. We'll logic through that one as well. Alright, the second derivative test essentially tells us we have a critical point. And then at the critical point, the first part tells us at the critical point the function is concave down. What does concave down look like? This. If this is a critical point, then this is clearly a max. This double I tells us that if we have a critical point and then the function is concave up, so concave up looks like this, yes? So here, this is a minimum. And then if the double derivative is 0, then we can't really say anything about it. The result's inconclusive. We gotta check something else. Alright, so let's look at applying some of this stuff. So something called optimization. So what can we do with that? How do we, like what? So the goal. When you say to optimize something, what you're saying to do is you're trying to make it minimized or maximized. So we can use the stuff that we literally just did, finding extrema, to do this. So first thing you always want to do, draw a diagram. No matter what, draw a diagram. Somehow define variables, and write the relationships between those variables, otherwise known as formulas. For optimization, you want to make it so that your formulas are all, and equations are all with respect to one variable, because right now we're doing single variable calculus rather than multivariable, which you don't exactly want to do right now if you're in high school taking AP calculus. Actually, some of you might want to, but anyway. And then you just repeat that max and min process and essentially find the maximized or minimized version of whatever you're trying to find, and then you'll be good. Okay, so let us do a quick little example then. So, let's say that you want to make a box-shaped room because reasons. And the length of it is 4 times the base. So let's just start doing that. So let's start drawing it. I did a lot of visual arts as a kid, so drawing these things wasn't too difficult for me, but I understand that not everyone has that experience. So what I would say to that is draw a lot. Just draw. Try to draw these things. That'll help a lot. As you keep trying to draw them, it also at least forces your brain to think about what is this thing supposed to look like. So let's just say this is a room, and the length and the base are related, right? So the length is 4 times the base. So this is the base because it's smaller, and this is the length, which is 4 times the base. And then the height is just, let's just call it h for height. Alright, so we know a few things. The first thing is that the material for the walls is $6 per meter squared. And the material used for the roof and floor are the same, because let's make the problem easier. And it's going to be $10 per square meter. So the room's going to have a volume of 50 meters cubed. What dimensions will minimize the cost? So this is a cost optimization problem. So I'm going to underline some of the information so we can know things. Goal is minimize. Volume is that. Length is 4 times the base. Wall is just height. I mean, wall is just height. The height of the wall is just h. Alright, so we have volume, so let's just get an equation for volume. So volume is base times height, or length times base times height, right? Well, the length is actually equal to the base. So, I mean, 4 times the base. So we can just say 4b times b times h. In other words, 4b squared h is the volume. Okay, so what are we even trying to find, though? We're trying to actually calculate the surface area, because we're putting stuff on the walls and we're putting stuff on the roof and floor. And because we can, the roof and the floor have the same material, so it makes it easier rather than 3 things. Okay, so the surface area is going to be, let's see, the base times the height. That happens twice, right? And then the this other longer wall is going to be, so this wall, the area for that is 4b times height, and that happens twice as well. And then we have the area for the base, like the bottom part in there. And then the roof right there. So we're going to do that real fast. Oops, that got messed up a little bit. Let me just change that a little, then go back to actually streaming. I just accidentally hit a thing. Okay, there we are. So let's see. That's going to be b times 4 b. So that. So yes, I know that I can write this all with a 2 factored out, but there's a reason I'm doing this. And that has to do with what we're going to do with it later on. Okay, so what is the cost? Let's just say C as the cost. So the cost is going to be, the cost of this is just going to be $6 per square meter, right? So 6 times this thing. And then this part is going to be 10 times that. Alright, so this is 12 BH plus, I should just combine those. 12 times 5 BH. 12 times 5 is 60, so 60 BH plus 80 B squared. Okay, so question. What can we do here? The H, we can actually get rid of that because this volume is 50 meters cubed, right? So if we were to set that equal to 50, then we can divide things and we get H equals, let's see, 50 divided by 4, that's going to be 25 over 2. And then B squared is just there. Alright, so let's just plug that in. 60B times that equation. I'm just going to write C of H equals, that's going to divide out, that's going to divide out, 30 times 25. Let's see, that's 75 times 10 to 750. So we get 750 over B plus 80B squared. Okay, so I'm going to erase some of the stuff because of space. Actually, if you need to, take a quick picture of this. Or pause it if you're watching the video version instead of the live stream version. Okay, gonna erase it. Okay, so C of H equals that, and we want to find the dimensions, right? The dimensions that minimize the whole thing. So I'm just gonna write this up here. Okay, so how are we going to, actually I'm gonna write this a little bit differently. I mean, since we're taking a derivative, this makes sense to do. So let's take the derivative. So that we can find the minimum of this. So 750 times b to the negative 1 plus 80 times b squared. So negative 750 b to the negative 2 plus 160 b. Alright. That's going to equal 0. So let's see, what can we do with this? 160b equals 750 over b squared. I'm just going to write it that way. multiply b squared to both sides, divide by 160, we get b cubed equals 750 over 160. This is going to be crazy. Okay, so b cubed equals 75 over 16. So b equals the cube root of that. I really should have tried this before I did this, but oh well. So we got that. Now we have to find all the other dimensions. So we have height equals 25 over 2 times b. b is the cube root of 75 over 16. And we have the length is just 4 times that. Okay, so I'm just going to leave it like this. If you really want to calculate it out and stuff, feel free to, but this is already insane. So let's just leave it like that. If you have something like this on the AP test, you're probably either going to have it in a calculator section or it's going to be a non-calculus section and you'll just leave it this way. Alright, so let's move on to related rates, the last topic for derivatives. Then we're going to move on to integration. So the goal is to use rates or derivatives that are related to solve problems. So very similar guidelines and stuff for optimization and related rates, except for the fact that you're going to have implicit differentiation happening. So you don't actually have to write things to one variable only, because implicit differentiation lets you do whatever you want to. Then you find the needed value or values after that. Actually, chances are it's just going to be one value. Alright, let's look at this problem that I kind of found / wrote / modified / let's just read it. Okay, so what information do we have here? So, Team Rocket, here's that Ash and friends are going to Saffron City. So they want to set out there to catch Pikachu because apparently that Pikachu is special. I don't know why, but apparently it is. They usually have a Meowth balloon, but decided that they would go with a Voltorb instead. So Voltorb is a sphere, if you're not aware of what Voltorb looks like. Essentially, it looks like this. Okay, really quick sketch of a Voltorb. It doesn't look great, but whatever. So, let's look at what information we have. So they're going to use a Voltorb-shaped balloon, so sphere. Oh, I think I spelled sphere wrong. Yep. Well, anyway, sphere. Start pumping air into it at this rate. And it's going to be able to fly once diameter reaches 5 centimeters. How fast is the radius increasing? So, let's look at what we're given and what we need to find. So what we're given is air is pumping in at that rate. So what is that referring to? Well, meters cubed per second. That gives us a hint that this is the volume of air going in. So we know that dV/dt equals 10 m cubed over 10 meters cubed per second. I'm not going to have the units there just for so it's not messy. Okay, then what else do we know? Then we know that can fly when diameter equals 5 centimeters. So I'm just going to say radius equals 5 or 2 because, oh, for one thing, I put you want to use that. So that's a hint. You're going to use that. But also, whenever you're dealing with volume, you usually define it with radius, right? Not with the diameter. So If you see a diameter, it's always good to just do that so that you don't forget to do that later, because chances are you will use the radius instead. Okay, so what are we trying to find? We're trying to find the rate of increase for the radius, dr dt, when what? When the balloon is able to take flight. Since we're doing dr dt, you want to use r instead of d, most likely, so I'm just going to say dr dt when r equals 5/2 centimeters. Oh, that should be meters. Whoops. Oh well, anyway. So we're going to need volume. So volume of a sphere is 4/3 pi r cubed. So let's do stuff to this. We know that we're going to need dv dt somehow, so let's just ddt this entire thing.